We've seen that a lot of information can be gathered by graphing the molar Gibbs energy against temperature at a constant pressure, and we're going to examine one last piece of information that we can get from that, and that has to do with the critical point. Now, we've seen that in the PV diagram, looking at isotherms, there is a critical isotherm that separates the liquids from the gases on that PV diagram, and on that particular isotherm, there is a point at which the slope is zero and the second derivative is zero. I'm not going to redraw it here, but I hope you will recall that that is the case. What we're going to do is look at what that means on this new diagram that reflects the change in the Gibbs energy, the molar Gibbs energy, with respect to temperature. So once again, we'll be using the fact that the molar Gibbs energy change with respect to temperature is equal to minus the molar entropy. And I also will want to reference the fact that the change of the molar entropy with respect to temperature at constant pressure is equal to 1 over T times the constant pressure heat capacity. Now, the reason I'm using both of these is that I want to compare the vapor and the liquid. And I know, for example, that the molar entropy of the vapor is always going to be greater than the molar entropy of the liquid. All right, but what this second piece of information tells me, though, is that the rate at which the entropy is changing as a function of temperature is different between these two also. And in fact, what we know in general is that the molar heat capacity at constant pressure of the liquid is generally greater than the molar heat capacity of the vapor. Now, what does that mean? Well, what this is essentially telling us is that while the vapor starts off with a steeper slope, the liquid actually catches up to it and gets a slope that is even more steep because of this relationship. So in other words, after these two have crossed, or even before they've crossed, at the very least, there will be a point at which their two slopes, their two values of entropy, can become equal. Okay, because the liquid is increasing faster than the vapor, so even though the liquid starts off behind the vapor, it eventually will catch up thanks to this relationship. All right, so what does this look like? Well, we know we can write down an expression for the entropy, the molar entropy of a vapor at some temperature T. And I'm going to write this relative to a temperature T0 because we're going to use the same reference temperature for both the vapor and the liquid. But for some reference temperature T0, I'm going to use this relationship here to write Cp of T over T dt. And maybe I should change this integration variable to something that doesn't match the integration limit of T. All right, so this is going to be an expression I can have. Now, I could also go so far as to say this heat capacity doesn't change very much with temperature. This actually is not true, but let's say we made that assumption, then we would end up with an expression that would look something like this, that the heat capacity at whatever temperature we like, I'll call it at T, times log of T over T0, and this heat capacity is relevant to the vapor. So I want to make sure that I've labeled it as being for the vapor, would be equal to this. All right, now I could do the same kind of calculation for the liquid. And I'm going to run this sort of from right to left so that we can bring these two together. All right, so I could say that the heat capacity for the liquid, if I run it from some reference temperature to a higher temperature, T, of Cp of the liquid, now at some temperature T, divided by T dt, this will represent this value here. And that again, if I assume that the heat capacity of the liquid is roughly constant over this interval, this could be written somehow like this. All right, so in essence, we have two factors here that give us the log of this ratio. And what we're looking for is the particular temperature at which these two might be equal. So at that point, we would find that the molar entropy of the vapor and the molar entropy of the liquid would be equal. And if they're equal, that means that the slope of this free energy curve, this Gibbs energy curve would be equal also. Well, let me draw what this looks like, because it's a lot of math without drawing any pictures, and it's good to look at a picture of this. Right, now I'm not going to draw the curve for the solid anymore. I'm just going to focus on the liquid and the vapor. So the vapor is going to come down, and it's going to be relatively steep over here. Draw it something like that. Okay, it may or may not cross the liquid before this, but we'll just say the liquid comes down, and it similarly gets, after it crosses, it gets more steep because of this effect, because of the effect that its heat capacity is going to be greater than that for the vapor. So after this crossing point, we could reach a temperature, and I'll say this is the temperature, at which we find that the slope of these two curves, drawn in red here, is roughly equal. Okay, so the slope there is equal. And you might say, well, big deal, so what? Well, this is at a constant pressure. And I guess it's probably a good idea for me to label this curve so that we know that this is the molar Gibbs energy and this is the temperature over here. So this is at some constant pressure. Now what's going to happen as we change the pressure? Well, we know as we change the pressure, it will change the liquid curve a little bit. It'll move it out slightly. Okay, but it will move out the gas curve a lot more. So it will push this gas curve out somewhat higher. All right, so now I want you to imagine that we could arrange circumstances in such a way that we find the magic pressure at which not only these two Gibbs energies have the same slope, but they actually intersect at that point where they have the same slope. So now I'm going to have this sort of situation where I've got a liquid that's coming across like this, and I've got a gas that's coming down like this, and there is a point down here at which their slope and their position match. So let me label this curve so that I've got vapor here and liquid here. Okay, so the slope matches at this point. Now what does that mean? Well, we know that what this means at this point, since that intersects, is that the Gibbs energy of each of these phases has to be equal at this point. So in other words, this is a phase transition point. All right, but we haven't encountered what it means when that coincides with the vapor of the entropy, molar entropy of the vapor and the molar entropy of the liquid being equal. Okay, if this is also equal, because of the definition of the Gibbs energy, this also implies that the molar enthalpy of the two phases is going to be the same. All right, but we also know that, for example, the molar entropy is going to be equal to the molar enthalpy of vaporization at the temperature of vaporization, and that's what this point represents now, is the temperature of vaporization. So if this is equal, and these things are all equal, it will also turn out that the molar volumes of these quantities will be equal. So molar volume of the vapor and the molar volume of the liquid will be equal at this point. So I've got free energies, Gibbs energies that are equal, I've got entropies that are equal, enthalpies that are equal, and molar volumes that are equal. So if all of these quantities essentially have the same value, and this, by the way, is the same because I know that my molar Gibbs, that this quantity, which equals the molar volume, is going to be the same in both of these cases. So if all of these things are equal, that means that we really can't tell the difference between a vapor and a liquid. So in other words, the vapor and the liquid are indistinguishable. So this special point that we have found, this point here, is something that we call the critical point. And in particular, if we go to temperatures higher than this critical point or to pressures higher than this critical point, under those circumstances, we no longer can tell the difference between vapor and liquid. In fact, what we will have then is a special kind of phase that we call a supercritical fluid. So supercritical fluid is going to be in that range that represents higher pressure and higher temperature than the critical values of those two things. So this critical point actually has a very fascinating thermodynamic definition, and we're going to see how it's manifest in a phase diagram in the next lesson. But I hope you can understand sort of what this construction tells us in terms of how unique this point is, because it brings together all of these thermodynamic quantities as being equal at the same point between these two phases. Incidentally, we cannot construct a similar point between a solid and a liquid simply because we can never get the two slopes to match up at the same point. There's just physical limitations that mean that solids and liquids will never end up having the same slope, so we would never get this confluence of thermodynamic properties being equal at the same point.